Slow.
It's not
Get
even
okay.
short. It's like inch long.
So,
Like
so
that
as
short.
soon
It's
as
like
you can confirm or deny that there's something there, let me know. All right. So the first warm-up question. The warm-up's all about just understanding how rockets work. Yeah, yeah, that's a little distracting, but oh well. So why do we have fins on a rocket?
to keep it going straight up.
To keep it going straight up. And do they need to be on the back? Can you put the fins on the front?
It's
Like,
probably better on the back.
yes, yes, yeah. You need. In fact, if you put the fins up here, guess what the rocket would do?
Flip.
It would turn around and go backward. So, can somebody tell me how do the fins make it go this way, prevent it from going that way, prevent it from going this way? If I throw this rocket across the room like this, it's going to straighten out and fly like that with the fins backward. Anybody raise your hand if you can tell me how it does that? How does it do it, Ben?
Well, when it's like straight in the way it's going, it has the least amount of drag, so I feel like it's going to want to gravitate, have the least resistance.
But how does it know? How does it know? Oh, I need to turn like
It
this.
doesn't know the air.
I mean, couldn't it turn like this and have equally small drag?
It's got a big brain.
Does the air push against the fin?
Yes.
Like it cuts through the fin?
So as it moves through the air like this, there's drag all along this side. And part of what causes drag is cross-sectional area. And which part of the rocket has the biggest area?
The left.
The back.
Yeah.
So as the air pushes on this, it's going to push on every part. And which part does it push on the most?
The left.
The fins. So the fins get slowed down, and that points into the wind. So even if I throw this backward, if it's, or I drop it from a tall building, it's going to eventually kind of wiggle sideways, and these are going to get pushed more than this, and it's going to turn around until it's going like that. And the advantage
Why'd you cut holes in them?
Weight
in these,
savings.
so this isn't working very well, but if you, maybe you can see this in the camera, see how this fin is kind of wide,
Whoa.
and these
Like me.
are nice and thin. And if you take a hot nail and heat it up with a torch and push it through here, it sort of welds the two sides of the plastic together. So that was just my way of keeping this nice and thin. So why do you want the fins to be thin?
So they don't make much drag.
Right. So once it is turned like this, you've got this cross-sectional area, but you know this fin right here, this fin right here doesn't really add much from this perspective. It's really skinny. Now if it's fat, then it adds some significant cross-sectional area. And this one over here, you know, is real thin. So you want your fins to be thin and rigid, but then if it starts to turn like this, then you can see this, and the oncoming air can sort of see it and push against it and straighten things back out again. So you need fins as far back as you can get them. The farther back, the better. The other thing that I'm going to recommend. Oh, has anybody checked? Is this actually? It's working. Okay, good. Whew. I don't want to do this again. In this picture, this is just an example picture of kind of a decent rocket. Your goal is to make the rocket stay in the air for as long as possible. So if you could do better than decent, that's great. These fins are what we used in Physics 100. I had a bunch of old DVDs and I brought them in, and you can cut a DVD into 3 equal parts and glue that onto your rocket, and those work pretty well. But most people have some old CDs or DVDs lying around. I'd recommend bringing some of those in if you can't find anything better for fins. So the other,
Why is there a sponge there?
the sponge,
It absorbs heat.
it's, I think of it more as a piece of foam, a foam pad. The foam pad is for holding the Pocket Lab Voyager sensor. So the main thing we're going to get from this is data on how high it went, or at the very least how long it took to get to the top and then come back down. So this sensor, you'll hook it up to a Chromebook or maybe your phone, probably a Chromebook or a laptop, and stick it in here like
So we all share the
so.
pieces of foam.
No, I'll cut more pieces of foam, and I've got more sensors, and then this goes in here. And the foam is to prevent the sensor from getting destroyed. And one of the requirements for your rocket is however you build it, you have to provide a 10 centimeter long area that's the same cross-sectional area as a 2-liter bottle for housing this foam. The other thing we need to do, and Mr. Chase and I have debated whether it really needs to be done, but I think it does, is we need to poke holes in the side, kind of like the holes I poked here. So I'll bring in a nail and some vice grips and a torch, a blowtorch. And you can heat up the nail and just poke the nail through this green part or through whatever part you have to contain that. And that's to allow air to get in and out. We're not really certain you need it, but we'd rather err on the side of caution, because as this goes up, this thing is going to measure altitude, and it's going to do it with pressure. So where's there more air pressure? Up high or down low? Down low, because air pressure is from the weight of air. If you have a cubic meter of air at sea level, it's about 2.5 pounds. It's really pretty heavy. And if you think of all the cubic meters of air that are on top of us, it's like we're at the bottom of the ocean, really, an ocean of air. That's a line from a National Geographic. We live at the bottom of the ocean. An ocean of air. Anyway, it goes on. It's National Geographic Cyclone, I recommend it. So anyway, as this goes up, the pressure around this rocket should decrease, and the sensor will pick that up. But I'm afraid that if we don't have holes and air can't move in and out, the pressure can't equilibrate between the inside and outside. So that's why we'll need those. So that's there so that the sensor can survive. You'll connect to it, you'll start it logging data. It's going to go up, it's going to disconnect from your device, then you'll reconnect after it's down, and you'll get the data. So I kind of forgot where I was. So we went over fins, the mass. This mass at the tip of the rocket, the front tip, why is that there? It's not there on here. This isn't an ideal rocket. It would be better if I'd take a rock and glue it right there, or duct tape it. Why? Why do you want it to be heavier?
So it has more force and the air resistance affects it less.
So yeah. If you put a bowling ball here, that wouldn't help. But if you put just the right amount of, no mass, it's not going to go very high. A little bit of mass here, it's going to go high. Too much mass, it won't go high again. So when it's launching, it's got to overcome this mass. It's got to accelerate more mass. But once it gets going, like Darian was saying, the drag is going to have less effect on it if it has more inertia. Just like a baseball, once you get it moving, it's going to go farther than a wiffle ball. If it's too heavy, if it's like a bowling ball, you can't get it moving in the first place. So the mass is going to give it more momentum. But the other thing, if I didn't have any fins, I could make this go straight just by adding weight to the front. Has anybody ever made spears and thrown spears in your yard? I know some of us have.
I mean, I've thrown sticks
So
and stuff.
if I made this spear, this pencil is a spear, and I threw it, I tried to throw it to Darian and stick it through his heart. So would it fly straight and hit him like this and embed? No. Now if I put some fletching on the back and I shot it through a dart gun or something, it might go. But without any fletching, where could I put a weight to make this go straight?
The middle.
In the middle? No, Darian.
Yeah.
On the front.
Wait, what is the front?
So
like,
the
make it
front.
sink?
What's that?
Wouldn't it make it sink?
Well, it might, but if you throw it fast,
That's true.
what it'll do is, and this is when I need a hammer. Has anybody ever thrown a hammer?
Yeah.
Like, somebody, yeah, they're kind of hard. They're unpredictable. They don't rotate like this. A hammer does not rotate around its center geometrically. The center of rotation of a hammer is where?
Or center of mass.
About the head.
It's by the heavy end. So if this is the heavy end of the hammer is going to rotate around more like this. The handle is going to make really big circles, and the head makes small ones.
So you
And
can whip someone with the handle.
and why that is kind of complicated. We could spend a lot of time talking about it, but just know that in space or in the air, when something rotates, it always rotates around its center of mass, and the center of mass is on the heavy end. So if you imagine this spear or whatever it is, just rotating around where my fingers are right there, what we've got now, if the air is blowing at it, we've got a little end and we've got a big end. Which one's going to have more drag on it? The big end, and that's going to get pushed downwind, and the little end is going to get pushed upwind. So by having the center of mass really far forward, that's going to make this fly straighter too. It might start flying like this, but then the wind's going to push on all of it, but this is its center of rotation, so it's going to go like that as it flies. So has anybody ever shot bottle rockets? You know, the fireworks? It's a little stick with a motor on it. Where do you put the motor on the stick? Do you put it at the middle, the back, or the front? The front, and a couple of things that does. That puts all the weight toward the tip. Then you have this really light stick back here. So if it ever does turn like this, the wind just blows the stick back down and it goes straight. But if you put some fins on a bottle rocket, it'd probably go even straighter. All right, so far, hopefully you've seen, if you want to make this go high and go straight, it needs to have weight as far forward as possible. And it needs to have fins on the back. What makes it go in the first place?
The water.
So how does the water make it go, Darian?
You pressurize it and then you release it.
So you'll bring this to me with water in it, and probably about a quarter full. I'll put a plug in right here. Turn it upside down. The launcher will clamp on. It's got 3 jaws like that. And then we'll pump it up so there'll be 100 psi in here, 100 pounds per square inch more than the outside pressure. And then you'll pull a little cord, and the jaws open up, and then the plug gets pushed out. And what does the water do?
It goes down.
What makes the water go down?
Pressure here.
The pressure, basically the rocket pushes the water down, right?
Yeah.
So what does the water do?
Pushes the ground down.
No.
Ground
Pushes the rocket up. So you're right. The water does push the ground down, but that's sort of beside the point. So the rocket pushes the water down, and the water pushes the rocket up. And if you use soda, you might get a little more pressure, but that's illegal in this particular scenario. You can use tap water and 100 psi.
Sparkling water?
But you're right, sparkling water, that would give you a little advantage maybe.
Yeah, I want to use that.
Mentos and Coke, that would
Yeah.
give you an advantage, but no. We're trying to keep it an even playing field. So what if you didn't have water at all? If it was just compressed air, would it go anywhere then?
A little bit.
So what would be pushed out the bottom then?
Air would push
Air,
against the ground.
right. And then the air that's getting pushed out would push against the rocket and make it up. Would this work in outer space where there's no air around? If you filled it with air
No.
and then you launched it,
Yes.
Yeah.
would air come out? Yeah, it would get pushed out.
For it to push against.
Well, it doesn't matter. This is like a rocket. Its exhaust gets pushed out, and the exhaust pushes the rocket forward. All right. This is good. These are good things to get out of the way. So I've been over all this. What makes a rocket go up? That's the action and reaction. You need fins at the back because that makes it go straighter. You need mass at the top because that makes it go straighter and gives it more momentum to overcome the air resistance. And then, okay, so let me go over the guidelines and restrictions so that people at home will know what we're doing. Maximum group size, 3 students. So you can work alone or in a pair or 2 or 3 people. Pressure chamber will be made of at least 1 uncompromised 2-liter bottle. So what I mean by that is this is an uncompromised 2-liter bottle. If you scratch it up a whole bunch, you start to cut into it, or especially if you cut into it a lot and then you think you're going to duct tape over it or hot glue over it, when we pump it up, the best thing that'll happen is it'll explode, and that'll be really fun. But what'll probably happen is we'll pump it up and it'll just start to go and then I'll have to go remove it from the launcher. If it explodes, then it just removes itself from the launcher, and again, that's sort of exciting. But if you cut it, then it's just no fun, and it doesn't work. So that's the pressure chamber. A protected capsule area, I already told you about that, to hold the sensor. It's got to be at least 10 centimeters long because that's how thick the foam is. The capsule area must have perforations. I already mentioned that. We'll do that with a torch and a nail. The neck must be free to accept the jaws of the Pittsco Aquaport launcher. So that just means this area right here, the jaws grab on and then they release. So don't put a bunch of stuff on the rocket right there. And then it'll be okay. No dangerously pointy objects. Every time we do this, somebody wants to have a nail sticking right out the tip. And it's going to be plenty dangerous even if we don't have the nail. If one of these hits you on the head coming down, you're going to be, you're going to have a concussion regimen or worse. All provided energy will come from 100 psi of added air pressure, so no carbonated water. I will provide 2 2-liter bottles. I'm going to go to Essex Beverage and buy, they're 5 cents a piece. I can get a whole bunch of 2-liter bottles. It's way easier than having students bring them in. We'll have duct tape, cardboard, clear tape, hot glue, lead tire weights. So I should have put an asterisk next to both of these. Hot glue, guess what my concern is with hot glue?
Melts the plastic.
Melts the plastic. If you just take a hot glue gun on high and you start adding some hot glue here thinking you're going to glue your fins on, it's going to shrivel up and it's going to be really nasty looking. So if you do want to hot glue something on, like if you want to hot glue a piece of a CD, then what you can do is first put it on low. A lot of hot glue guns have a low setting. And put it on the CD first, let it cool down a little bit, sort of experiment to see if it's getting a little bit cooler. And when you think it's not too hot anymore, then stick it on here. And then take a nail or a toothpick or something and kind of smear the glue. It would help if you sanded the surfaces first, not so much that you compromise the bottle, but sand them, just kind of rough things up to get it to stick. But don't just hot glue right on the bottle. It'll definitely, except for right here, which is a place where you shouldn't be gluing, and right here, it'll shrivel. But these are the 2 places where the plastic is thick enough that it won't shrivel up. What else do I have? The lead tire weights. So those are poisonous. Lead is really bad for you, but it's a nice weight. And I got a bunch from Whitcomb's a long time ago. I was going to use them on a trebuchet. And you don't eat them. And when you're done messing with them, wash your hands and don't suck your thumb and that kind of thing. Some crucial design things. The fins. The fins are super important, but they're also just troublesome. You can see these are probably not what you would want for fins. They're pretty good except this one that's starting to come apart. And then I've got them duct taped on. So these fins, they're not coming off. Sometimes what will happen is people will glue CDs to these things just like that, and they'll rely on the hot glue. And then when we start to pump up the bottle, guess what happens to it? It expands and the glue pops loose. So I don't know. It might be better to do something like what I've done here with the duct tape. What else? Weight. Make sure you add weight as far forward as possible. Symmetry is super duper important too. If your 3 fins, if this one and this one, if they're closer together than that one is, you're going to have more drag on this side of your rocket, which is going to tilt it in flight. If you have something like I've got here, and you probably will, and you put this on and you don't look at it carefully, and it looks pretty good like this, and then you start to rotate it around, and you realize, I'll make it even worse. Looks like that from there. From here it looks nice, but then you realize this isn't going to go straight. It's going to be a little crooked. And it's going to have a bigger cross-sectional area, which means more drag. Symmetry, plenty of room for the insert. A lot of people don't allow enough room for this foam insert, but make sure that if you don't put it in your rocket, you can assemble your rocket and you've got at least 10 centimeters of space that are as wide as your rocket. Let me show you one other quick thing, and then I'm going to stop streaming. And this is you might want to mess around with this. This is Clifford Heath's water rocket simulator. Apparently this link doesn't work. So, yeah. So you have to Google it. Clifford Heath water rocket simulation. A lot of people have been to Clifford Heath's website. And right now everything is set to a 2-liter bottle with 800 milliliters of water, so it's like 40% full of water. It's 120 psi. We're only going to use 100 psi. The nozzle size, I think, is about right. That's the inner diameter of the nozzle. This loss factor, I have no idea what that is. I just leave it alone. Bottle diameter, I think, is about right. Drag coefficient, probably in the right range. And then dry mass. This is what the mass of the rocket would be when all the water is out of it. So if you put this on a balance, that'd be the dry mass. And this other stuff right here isn't anything I ever mess with. So if I submit simulation, gives me all the data, gives me the initial thrust, 481.5 newtons, average acceleration, almost 1,000 meters per second squared. But it gives me the apogee, that's the highest point, total flight time, gives you a little graph, some other interesting stuff down here. But the most useful thing about this is using it to dial in how much water to use. One thing you can do is you can put in a range of values. So instead of 0.8, I'm going to do 0.3 through 0.8 and then hit submit. And these are different volumes. It just sort of gives me evenly spaced volumes. This is the time it would stay in the air. And this is the height it would get to. And it looks like this maxes out right around here. So it looks like somewhere around 467 cc's is good. So then I can go to here and put in 0.47. Then I can do a range of dry masses, 50 to 150, and submit the simulation. And take a look and see which one's going to keep it in the air the longest. According to this, it would be about 134 grams. In my experience, heavier rockets than that actually work better. But don't take my word for it. That's just my gut feeling on all this stuff. So go back to the plan here. So really, you don't have any homework. The homework is we've got a test next Thursday, not 2 days from now, but a week from 2 days from now. You may want to review your packet. But right now, for the next 5 minutes or so, you might want to think about who you're going to work with on this. And if you want to bring in extra stuff tomorrow, if you're looking for weights for the rocket, I've got those tire weights. But another thing that works well is old batteries, like AA batteries or C batteries. You can try some different kinds of things. Definitely fin material. That's important to think about. And you could theoretically cut 2 2-liter bottles and then seal them together to make an extra long one. I haven't had a student successfully do this in over 10 years. Usually when people try that, they explode. And you can read on the internet about how to do it, but it is possible to make an extra long bottle so you have a 4-liter bottle or a 6-liter bottle instead of just a 2.
Can we bring in as many bottles as we want?
You can bring in as many bottles as you want, but don't count on my hot glue and my duct tape is never going to allow you to seal these together. You would have to go home and do some special gluing to make that work. And it might just explode anyway. All right, that's it.